Alright, so we talked about series circuits, now it's time to talk about parallel circuits. So what we've got here is a parallel circuit, a really simple one. This one would be a circuit that controls two lights, light there and a light there. There ought to be a switch in here somewhere. If I had drawn this properly, probably I'd put a switch right about there, just so that you can actually turn this on and off, but whatever. This is just to show you the idea of a parallel circuit, which is basically the idea that there's more than one pathway through which the current can flow. Remember, in a series circuit, there is only one pathway, and all of the current must flow through that pathway. But in a parallel circuit, there is more than one pathway. So you could have the current go this way, or you could have the current go that way. And then as they come back out of the branches, they rejoin to return to the power supply. So anyway, that's the basic idea of a parallel circuit. So let's talk about some specifics. All right, so potential difference, let's start with that. You may recall that in a series circuit, the potential difference gets split among the components. So whatever the potential difference is here in the power source, you split it up among the components. So if this was a series circuit and these guys were in series with each other, which they're not, but if they were, then this one would get part of the potential difference and this one would get part of it, and then the sum of these two would equal this one. Not the case in a parallel circuit. In a parallel circuit, say you've got a certain brightness here with this bulb, and let's say that these two bulbs are identical to this one, but they're connected in parallel. And let's just suppose that this is a 3-volt power supply, and that these bulbs are meant to operate at 3 volts. All right? So they are at their full brightness when they have 3 volts of potential difference. Now notice, if I were to hook up a voltmeter in parallel right here, you may notice that the shortest pathway from the power source through the voltmeter, this imaginary voltmeter right here, would not include any components. You might also notice that if I went this way, it would include that component, and if it went this way, it would include that component. So the voltmeter is hooked up across, quote unquote, the power supply, but it's also across this load, and it's also across this load. I only point that out because the rule and what actually happens in parallel circuits is that both branches get the full voltage from the power supply. This also means that more energy is being used up in a parallel circuit than in a series circuit. So your battery will run down faster. That's the trade-off. However, both lamps will operate at full brightness. So you get full brightness here, full brightness here. So these guys each get 3 volts. 3 volts, 3 volts. Interesting. All right, well that's how it works in a parallel circuit. Potential difference, it's the same in all the branches, as long as they are hooked up in a manner similar to this. If you find a parallel section of a circuit somewhere in the middle of a bigger circuit, then it's a little harder to figure out exactly what the voltage is. But when you have a simple one like this, this lamp gets 3 volts and this lamp gets 3 volts. And since they're identical lamps, they will also have the same brightness. They will be lit up fully. All right, so just to reiterate the advantages of connecting lights in series rather than in parallel. First advantage, the lights operate at full potential difference, so whatever their intended volt rating is, that's what they get. So they will operate at full potential difference and they will have full brightness. It also allows for the setting up of independent switches, and that's what I've got pictured here. So you can have, in a parallel circuit, you can have separate switches for different lights. Whereas in a series circuit, one switch controls everything. Everything's either on or off. There is no separate switching on or off of different things in the series circuit. So just as a schematic version of this, let's say that your power is coming from the power plant, goes through here. There's a bunch of transformers and things that make it usable in your house, but I skipped picturing those. So, and then it ends up at a ground outside your house when it's done. But the interesting part is here. So let's just say that this switch controls the main circuit, the main power. All right, so if this switch is off, which it is right now, incidentally, then these lights would be off. But if this switch is on, then these lights could be on, but not necessarily. So then what I've got here pictured is a parallel portion of a circuit that breaks off here, goes through this switch to this light, and back again. All right? And then I've got a second parallel circuit in green that goes through this other switch, and to this light, and back again. Again, this is in schematic form, but this is just diagramming what might be going on in your house, behind the walls, in a sense. All right, so this switch would control both lights, and if it's off, both lights are off. But if this switch is on, let's just say we turn that switch on, then either of these lights could be turned on or off by those two switches. Right? If this switch is on, this light comes on. This switch is on, this one comes on, and vice versa. If they're off, they're off. But so one of the big advantages of parallel wiring is that it allows you to have independent switches for different lights. That's pretty cool. All right, on to current, and we'll try to wrap this up quickly. The current in parallel branches of a circuit is not the same as in the main circuit. All right, so there is more current in the main circuit coming out from the power source, going into the power source. The current here is the same as the current here, but as soon as you break into a branch, the current splits. And the way that it splits is based on the resistance in that branch. So if the branch has more resistance, less of the current goes down that branch. If the branch has more resistance, more resistance, less current. If there's less resistance, there's more current, because of course resistance is how much current is allowed to flow, or how hard it is for current to flow. So more resistance means it's harder, and the current is going to take, most of the current will take the easier path. And you can calculate that mathematically, which way it works. I just went with two identical lamps here, so that the current would split evenly. Half of it goes this way and half of it goes that way, since the resistance is the same in both branches. So it splits, half the current here, half the current here, assuming these are identical, and then it rejoins again, and down here you would have the full maximum current going back to the circuit. All right, so the total current is the sum of the current in the branches. Branch 1 plus branch 2 equals main circuit. All right, and then lastly, and this is a bit complicated, we'll do more with this calculation in class. I'm not going to do a practice problem on here because it will make the video too long. But in any case, the inverse, so in a series circuit, you add up the resistances to get the total resistance. So if this was a series circuit, resistance 1 plus resistance 2 equals total resistance, and that's it. If these were in series, but they're not, they're in parallel. So these are two resistors in parallel, one through here, two branches, one power supply. So the way the math works out, without getting into all the details, you have to do the inverse of the total resistance is equal to the sum of the inverses of the resistances. It's a little weird, but that's how it works. So you could add up however many resistances you have here in this form. Now, if you only have two, R1 and R2, you can rearrange it. All right, rearrange it, and then you get this other equation right here once you do some algebra on that mess. All right, so I could show you the steps of this in class if you guys want me to, but if you do the algebra to like get a common denominator and rearrange this all and get it all set up, you end up with this. So R1 times R2 divided by R1 plus R2. I'll tell you what, I'll do a really simple version of this. Let's say both of those resistors are 10 ohms. 10 ohms of resistance. So then the RT would just be 10 times 10 divided by 10 plus 10. Sorry, that's bad writing. So that's going to be 100 divided by 20, which is 5 ohms. So you immediately notice something very odd. The way that this math works and the way that this works in reality physically, I cannot tell you how this works exactly, but mathematically you can see if you take two resistors and connect them in parallel to each other, then their combined total resistance in the circuit is less than either of the resistors by themselves. 5 ohms is the combined resistance of this thing. All right, even though each one by itself is 10 ohms of resistance, the two of them combined in parallel have 5 ohms of resistance. So let me just write this down, pause and write, and then I'll be right back with you. All right, so there it is written for you. In parallel, the total resistance of the parallel branches is less than either branch alone. All right, cool. Sorry this video got a little bit long, but it's got a lot of information about parallel circuits, and they're kind of complicated. So that's all for this video. Thanks for watching, and we'll catch you in the next one.